In today's lecture, we are going to see the discussion on some important physical quantities of interest in simple harmonic motion. Actually, there are four important quantities which are invariably used in the discussion of simple harmonic motion of a particle. And these are displacement of the particle during SHM, its velocity, its acceleration, and its energy. Actually, to keep the lecture in the proper time interval, I will discuss only the first three important physical quantities of interest in simple harmonic motion. That is, we will see in this lecture the idea of displacement, velocity, and acceleration only. And in the last of the lecture, actually, I will solve an important numerical problem so that your concept which will be developed earlier will be clarified. So don't miss to watch the solution of the problem which will be provided in the last of the lecture. That will be a very important problem, and you will learn so many things when you will solve that problem. Not only you will learn about simple harmonic motion, but you will learn so many things which will be very helpful in solving the other problems. Okay. So let us start to know the first important physical quantity of interest in simple harmonic motion, and that is displacement. You can see it here. You know that if we consider there is a particle of mass m oscillating simple harmonically on this straight line, let us say this straight line is x prime, okay, about the equilibrium position O. Then you know at any time t, the particle is, let us consider at point P, which is at a distance x from the equilibrium position. Then this x is actually called the displacement of the particle. Okay, it is called displacement of the particle at time t. And you have seen in the solution of simple harmonic motion, equation of simple harmonic motion, that the simple harmonic motion can be represented in terms of the sine function or cosine function defined by this equation, x equal to a sine omega t plus phi. Okay. You know this phi is called phase constant, or it is also called initial phase or epoch. And you have learned earlier that the value of this phi depends on our selection of reference time t equal to 0. It means what is the position of the particle when you take t equal to 0, that actually determines what will be the value of phi. So for simplicity, in the present lecture, for all calculations, I am considering that when the particle passes through the equilibrium position, or you can say when the particle is at the equilibrium position during SHM, then we consider t equal to 0. This is just an example for simplicity. Okay. So you can say that t is equal to 0 when x is equal to 0. Now imposing this condition on this equation 1, you can find what will be the value of phi in this particular condition. Okay. As you can see, taking t equal to 0, we have to put x equal to 0. So let us substitute these two values in equation 1. And so this will be 0 equal to a sine phi. But you know a is the amplitude of this SHM, and so it is not 0. Therefore sine phi will be 0, and if sine phi is 0, you know phi is equal to 0. So in this condition, the displacement x is given by a sine omega t, where you know the time period of this simple harmonic motion is capital T given by 2 pi over omega. Okay. Actually, in this figure, I have shown the graphical plot of the displacement x in against of t. This is nothing, this is simply the graphical plot of the sine function, that is sine omega t, in against of t. Okay, in against of t. So you can see at t equal to 0, the displacement is 0. Again at time t equal to pi by omega, it is 0. And again it is 0 at 2 pi by omega. And at time 2 pi by omega, one oscillation is completed. So in one oscillation, in the half oscillation between time 0 to pi by omega, the displacement is positive, and between the time pi by omega and 2 pi by omega, it is negative. So displacement in this case may be positive and negative both. Okay. Now we will see some important facts regarding this displacement. Actually, during simple harmonic motion, displacement is measured always with respect to the equilibrium position, and SHM takes about this equilibrium position. So definitely during SHM, the direction of displacement is always away from the equilibrium position. As you can see this first figure, I have shown that this O is the equilibrium position, and at any time t, the particle is at point P. Okay, and it is moving away from the equilibrium position. Then displacement is OP, and this OP is directed away from the equilibrium position. Okay. But in second figure, I have assumed that the particle is moving towards the equilibrium position. Okay. So velocity is from this P to O, but even then displacement is from O to P. So you can see the particle can move towards the equilibrium position or away from the equilibrium position, but displacement will be always away from the equilibrium position during simple harmonic motion. Okay. And this acceleration A is also always directed towards the equilibrium position. So you can say that acceleration is always in opposite direction of the displacement. It is anti-parallel to x. Okay. This is an important feature of simple harmonic motion, that during this, the acceleration is always towards the equilibrium position and displacement is always away from the equilibrium position. So these two vectors are just in opposite directions. Okay. Now it is clear from this expression for displacement defined in this equation 2 that if you know the value of t, it means time t is given, we can easily find what will be the displacement x. It means when t is given, you can find x. And its converse is also true. If x is given, we can find t. This is obvious from this result. Let us see some of the examples. So I have considered here, let us say, we know the value of x. Let us say x is equal to a by 2. It means the displacement is just half of the amplitude. Okay? And we have to find what is the time when displacement will be half of the amplitude. For this, we will substitute the value of x in equation defining the displacement, that is x equal to a sine omega t. In this equation, we will substitute the value of x. As x we have assumed a by 2, so a by 2 is equal to a sine omega t. And at the place of omega, you can write 2 pi over t. Okay? Now this a and this a will cancel out, and therefore sine 2 pi by t times a small t, this will be equal to what? This is equal to 1 over 2. But 1 over 2 is equal to sine pi by 6. And so you can say that 2 pi over capital T times small t is equal to pi by 6. And so t is equal to capital T over 12. So at a time which is 1/12 of the time period of this simple harmonic motion, the particle will be just at the midpoint between the equilibrium position and the extreme position. That is, its displacement will be just half of the amplitude. Okay. Now let us take the converse situation. Now we consider that we are given a time t equal to capital T over 8. And we have to find what will be x when time is capital T over 8. So you can use the same formula. X is equal to a sine 2 pi over capital T into small t. But small t is given capital T by 8. So this t and t will cancel out. And your result is a sine pi by 4. This will also cancel out. Here it will be 4. And sine pi by 4, this is 1 over root 2. So x will be a over root 2. So you can see, if time is given, we can find displacement, and if displacement is given, we can find time. Okay. Now let us see the concept of the another important quantity of interest in simple harmonic motion, and that is actually the velocity of the particle executing SHM. Okay. In fact, it is obvious. If you know the displacement of the particle at any time t, simply differentiating this displacement x, you will get the velocity of the particle. This is a very simple fact. Okay. So you can say that velocity of the particle at time t, if it is denoted by v of t, then what will be this? This will be dx of t by dt. Now see, x of t is this much, this is a sin omega t, and when you will differentiate it, you will get what? Omega a times cos omega t. So this is velocity of the particle executing SHM at any time t, or in other words, you can say this is the expression for velocity of particle as a function of time. When you say v of t, it means velocity at time t or velocity as a function of t. Okay. So you can see this velocity actually varies in accordance with the cosine function. So the graph will be just the graph of cosine function, and variation of velocity in against of time I have shown in this figure. You can see actually this omega, you know that cos omega t modulus of cos omega t maximum, this will be equal to plus 1. Okay. And so the maximum value of magnitude of velocity of the particle will be omega a, and this is called actually the peak velocity. And so you can see that the maximum velocity I have shown here is either omega a or minus omega a. Okay. And this is the graphical plot. Now, if your aim is to find the velocity as a function of x, how you can find? It is very easy. You can see the expression. The velocity as a function of time is omega a cos omega t. And our aim is to find the velocity as a function of x. So we must remove this cos omega t as a function of x. And with the help of this equation, x equal to a sin omega t, this can be done very easily. You have to remove cos omega t. So let us find this cos omega t by using this equation x equal to a sin omega t. You know, cos omega t is what? This is a square root of 1 minus sin square omega t. But you can see sin omega t is x over a. So this will be a square root of 1 minus x square over a square. After taking the LCM, your result will be cos omega t is equal to a square root of a square minus x square over a. Now, we will substitute this value of cos omega t in this equation 3. Then you will get the expression for velocity of the particle executing SHM as a function of x. So, velocity of the particle when it is at x equal to x, which I have denoted by the symbol v of x, that will be what? That will be omega a times this much. But a in denominator and a in numerator will cancel out, and your expression for velocity will be what? This is omega times a square root of a square minus x square. Okay? So, in this equation 4, we have obtained the expression for velocity of the particle executing SHM as a function of x, and in equation 3 we have obtained the expression for velocity of the same particle as a function of time. Okay? And both expressions are very simple and you should remember it. At least you should remember this equation 4 for your further discussion. This will be helpful for you. Okay? Now, after getting the expression for velocity of particle executing SHM, now let us see some of the important points, some of the important facts regarding this velocity. Okay? As you can see, since velocity of the particle depends on x, that is position of the particle, so for different position, the velocity will have different value. So you can say that velocity varies during simple harmonic motion. I have considered here actually two standard positions where we will find the velocity. The first standard position you can take is the equilibrium position of the equilibrium position, O. And you know, when the particle will be at equilibrium position, then x is 0. And if x is 0, x square will be also 0. And you know, x square equal to 0 is the minimum value of x square. Why? Because any square will be never negative. So, minimum value of any perfect square is always equal to 0. Okay? And in the expression of velocity, you are seeing that before x square there is minus sign. So, it is clear from this result that when x square will be minimum, then velocity will be maximum. Okay? Because when we subtract less, we get large. Okay? And therefore, you can say that if the particle is crossing through the equilibrium position, its velocity is maximum. And what will be that maximum value? For that, you have to substitute 0 at the place of x square. And so, we can write in this condition V is equal to V max, and that is equal to plus minus omega A. You can also write only omega A, but I have written plus minus omega A. But don't be confused with minus sign. This minus sign does not affect the magnitude of velocity. It is for the direction of velocity. Actually, we take the velocity equal to plus omega A when the particle passes through the equilibrium position and moves towards rightward. When the particle is moving in rightward direction and it passes through the equilibrium position, then you say that velocity is omega A. But if the particle is passing through the equilibrium position but moving in a leftward direction, in accordance with this figure, leftward direction, then we take V equal to minus omega A. Value of velocity in both situations is same. This minus only indicates that the particle is crossing the equilibrium position in leftward direction. Okay? So we say that maximum value of velocity is when the particle is at the equilibrium position and its value is equal to omega times a, where you know a is the amplitude of this simple harmonic motion. Okay. Now another standard position during SHM of the particles are extreme positions, and you know at the positive extreme position x is equal to plus a, and at the negative extreme position x is equal to minus a. Okay, so in general you can say that at extreme positions x is equal to plus minus a, and this is actually the maximum value of x, and so x square will be equal to a square. Even when you take minus a, then this will be a square, and this is the maximum value of x square. And so according to equation 4, when x square will be maximum, you will get the minimum value of velocity. Okay, minimum value. And therefore you can say that at the extreme position during SHM, velocity of particle is minimum and it is simply zero. Okay, and that's why, since velocity of the particle becomes zero at the extreme position, this is the region that the particle returns back from the extreme position during SHM. Okay. So these were some of the important facts regarding the velocity of the particle during simple harmonic motion. Now we are going to see the calculation of the third quantity of interest in simple harmonic motion, and that is acceleration. Okay, you know acceleration is what? This is simply the time derivative of velocity. So we can find acceleration of the particle at time t by simply differentiating velocity v of the particle with respect to time t. So you can say that this a at time t is equal to dv by dt. But you know v is dx by dt. So when you will differentiate this v with respect to t, you will get d2x by dt square. Okay. Now as you have learned earlier that this v is equal to omega a cos omega t. Okay, and x is equal to a sin omega t. Okay, so substituting this value of v here or this value of x in this expression, you can obtain acceleration. This is a simple differentiation, and you will see that acceleration will be equal to minus omega square a sin omega t. This is acceleration as a function of time. Okay, but a sin omega t, this is x. So instead of this a sin omega t, you can write x. So acceleration at position x is equal to minus omega square x, and you can say this is the necessary and sufficient condition for motion to be simple harmonic, that acceleration of the particle must be proportional to minus x. And this result also implies that acceleration is always directed in opposite direction of displacement, as I have told you during the discussion on displacement. Okay, and so a proportional to minus x is the necessary and sufficient condition for motion of a particle to be simple harmonic motion. Okay. Now let us see some important facts regarding this acceleration of the particle during SHM. You can see acceleration of the particle also depends on the position of the particle during simple harmonic motion. So if you want to find its value when the particle is at its equilibrium position, then what will be this? You know, at equilibrium position x is 0, and when you will substitute x equal to 0 in this equation 5, you will get a equal to 0. So you can see when the particle is at the equilibrium position, then its acceleration is 0. But you have seen at this position, velocity of the particle is maximum, and that was actually equal to omega a. So this is a very important point. During SHM at the equilibrium position, velocity is maximum, but acceleration is 0. Okay. Similarly, if you are talking about the extreme position, at extreme position, displacement x is maximum, and that is equal to a. Modulus of x, you can write a, and it is its maximum value. So the maximum magnitude of acceleration will be equal to omega square a. So when the particle is at its extreme position, acceleration is maximum. A is maximum, this is a max, and this a max is equal to omega square a. But you have seen just now that at the extreme position, velocity of the particle is 0. So in case of simple harmonic motion, the point of maximum velocity corresponds to the point of minimum velocity. It means the point where velocity is maximum, acceleration will be 0, and the point where velocity is 0, acceleration will be maximum. Okay, this is very important facts regarding this simple harmonic motion. Okay, again you can see that minus sign in that expression implies that acceleration is always directed toward the equilibrium position, and so always opposite to the displacement. As I have told you earlier, that this A is always anti-parallel to x. Okay, and just I have told you that point of maximum velocity corresponds to the point of minimum acceleration, and point of minimum velocity corresponds to the point of maximum acceleration. Now, if you neglect the minus sign in the expression of acceleration, you can write A is equal to omega square x. And so you can say that omega is equal to a square root of A by x. But if t is the time period of simple harmonic motion, then omega is equal to 2 pi over t. And so t is equal to 2 pi root over x by a. This is actually the general expression for finding the time period of an oscillator executing simple harmonic motion. You can use this formula as a standard result for finding the time period of any system executing SHM. If it is executing linear simple harmonic motion, you can write that time period is equal to 2 pi a square root of displacement divided by acceleration. This is the general result. Okay. So the concept which we have discussed till now, this was just an elementary concept. Most of you have an idea of this already previously. But this, as I have told you earlier, that this playlist is meant for students of different levels. So here I am talking even in detail the simple concepts too. Okay. Now I am giving you a very important example, a very important numerical problem, and that will actually clarify your idea regarding this, regarding the concept which you have just learned. Okay. Let us see this problem. What the problem says. A block is resting on a piston which is moving vertically with a simple harmonic motion of period 1.0 second. Okay. At what amplitude of motion will the block and the piston separate? First of all, you have to read the problem accurately. If you read the problem in nice way, properly, then almost 50% of solution will be in your mind. Okay. Now, the second part of the problem says, what is the maximum velocity of the piston at this amplitude? What this problem says? You can see the problem says there is a piston. You can see in a cylinder there is a piston. This P is actually a piston. And on this piston there is a block of mass M. I am showing here this block. Okay, this is lying on this piston, and this piston is actually executing simple harmonic motion in vertical direction. Okay, it means this piston will move up and it will also move down from the equilibrium position. And as the block is lying on the piston, so along with the piston, this block will also execute simple harmonic motion. The problem says that what will be actually the amplitude of the motion of the block, so that the block and piston will separate. What will be the amplitude of simple harmonic motion so that the block will separate from the piston? Okay. Definitely you have learned about the condition when a particle resting on a surface loses the surface. The condition is when the normal force acting between the two surfaces is not zero. As long as it is not zero, the contact is maintained. But when the normal force becomes zero, then there is a separation between the surfaces. Okay? So actually, when you will solve this problem, apart from the concept of simple harmonic motion, this fact should be also in your mind. So let us first of all see what will be the equation of motion of this block. When you say equation of motion, it means we are going to find what is the net force acting on it, and how, getting the net force, we can write its equation of motion. Okay. Now let us see here. If you want to find what are the forces acting on this block, you can see. If I have shown this in this free body diagram, this is the free body diagram of this block, and you know one force acting on the block will be the force of gravity or the weight of the block, which will act in downward direction. The another force is normal force or normal reaction due to surface of this piston, and this is acting in upward direction. Okay, this is acting in upward direction. Okay. Now the block is performing simple harmonic motion in this vertical plane, and we consider that its acceleration is a. You know, during simple harmonic motion, acceleration is not constant. So this a is the acceleration at any instant. This is not constant. Okay. And let us see. If this block will move in a downward direction, block will move in downward direction. Let us see here. Then, you know, the displacement will be in downward direction, and so acceleration will be in upward direction. So according to this figure 1 in the free body diagram, the block is moving down from the equilibrium position. Let us say that this is equilibrium position and block is here. Then acceleration will be in upward direction. And if acceleration will be in upward direction, definitely this force N will be greater than mg. So in this condition, when the block is moving down and its acceleration is in upward direction, what will be the equation of motion? You can see this will be N minus mg equal to ma. Actually here I have considered the direction of N or A as positive direction. And so you can say that N will be equal to m times g plus a. But now consider this block is moving up from the equilibrium position. And you know, when the block will be in upward direction from the equilibrium position O, then its acceleration will be in downward direction. Okay, you have learned. And if acceleration is in downward direction, what does it mean? It means then mg will be greater than n. And so, in this condition, we will write the equation of motion as mg minus n equal to ma when the block is moving upward. Okay? And so, n will be equal to m times g minus a. So, in general, you can say that during this simple harmonic motion, the equation of motion of the block will be what? That will be n equal to m times g plus minus a. Okay? Plus sign refers that the block is moving downward from the equilibrium position, and minus sign refers that the block is moving up from the equilibrium position. So in this condition, you can see that the difference of n and mg, that is n difference mg, this actually acts as the restoring force which provides the simple harmonic motion to this block. Okay? And here you can see when we will take this minus sign, then we will get actually the minimum value of normal force. Okay? And according to our question, we have to find the amplitude when the block will get separated. Okay? But let us think about what should be the condition that during this motion the block and piston will be not separated. As I have told you, the condition for no separation between the surfaces in contact is what? This is normal force acting between the two surfaces must be equal to, must be greater than 0. Okay. So the condition for no separation can be written as n minimum is greater or equal to 0. In limiting condition, we must use the sign of inequality. Okay. But you can see the minimum value of n is m times g minus a. So m times g minus a should be greater or equal to 0 for no separation of the block from the piston. And you can say that g minus a is greater or equal to 0. This is not a, but this should be greater or equal to 0. And so g should be greater or equal to 0. Okay. And as a is not constant, so if you say that g is at least equal to a, at least, either or it is greater than a, it means you must take maximum value of a. Because if you will not take the maximum value, then when you take g equal to a, that will be not greater than a. Okay. So you can say that since a is not constant, so we can take the maximum value of a, and so for no separation of the block from the piston, the condition is what? This is g must be greater or equal to a. But you have just learnt that the magnitude of the maximum acceleration of a body or a particle during simple harmonic motion is equal to omega square times a. So the condition will be g must be greater or equal to omega square a. In other words, you can say that this omega square a must be less or equal to g. And so a should be less or equal to g over omega square. Okay. As in our problem, time period is given. This is given 1.0 second. So let us change this omega in terms of time period. You know, omega is equal to 2 pi over t. So this result will be a should be less or equal to gt square by 4 pi square. Now let us substitute the numerical value. After substituting the numerical value, you can see that a should be less or equal to 0.248 meter. And therefore you can say that the maximum value of A should be 0.248 meter, so that the block will not separate from the piston. Okay, it means if amplitude will be at most 0.248 meter, then the block will not separate it. But think, if the amplitude of oscillation will increase, will be larger than this value, then what will happen? Then the block will get separated. So the minimum value of amplitude for which the block will separated from the piston, that will be equal to 0.248 meter. So A minimum equal to 0.248 meter for separation. Okay, for separation. This is a very remarkable fact. You have obtained what is the maximum amplitude for no separation. The answer is 0.248 meter. And now you are saying what is the minimum amplitude so that the block will get separated. Answer is same. Limiting value will be same. This is just I am clarifying it. Let us consider you are moving on a horizontal surface of length L equal to 12 meter. And after that there is a big D. Okay. Now you start moving on this surface from A reaches to B. Okay. Now if anybody asks you maximum distance traveled by you is what, so that you will not fall from B, what will be your answer? What is the maximum distance? अधिकतम दूरी क्या होगा आपके द्वारा चला हुआ जिससे कि आप B से नहीं गिरेंगे? आंसर क्या होगा? Answer will be 12 meter. Okay. Now another person asks you what will be the minimum distance traveled by you so that you will fall from B. आप कम से कम कितना चलेंगे कि आप B से गिर जाएंगे? Answer will be again 12 meter. At this limit, when you say that what is the maximum amplitude so that the block is not separated from the piston, the answer is 0.248 meter. And when you say what is the minimum amplitude of this SHM so that the block will get separated from the piston, answer will be again 0.248 meter. Okay. So for separation, the amplitude of oscillation should be greater or equal to 0.248 meter. Up to this amplitude, 0.248 meter, the block and the piston are not separated. But when this amplitude will exceed this value, the block will get separated from the piston. So the minimum value for separation of the piston from block is same, and that will be 0.248 meter. Okay. Now in the second part of the problem, you have been asked that what is the velocity of the particle of the block when it will be just separated. What is the maximum velocity of the piston at this amplitude? Actually, the velocity of piston will be just equal to velocity of the block, because the block is in the contact of the piston. So when the block will just separate it, then velocity of the piston and the velocity of the block will be just equal. So, and you know, since this block is performing simple harmonic motion and the piston is also performing same simple harmonic motion, so the maximum velocity during simple harmonic motion you have learnt, this is omega times A. And we have to find this velocity when the block is just separated from the piston. And at that moment you have calculated that amplitude is equal to 0.248 meter. So let us substitute this, and at the place of omega we will write 2 pi over t times a. Now t is 1 second, so this is 2 pi over 1 times 0.248 meter per second. And after calculation you will get this is 1.56 meter per second. Okay. So I think you have clearly understand the solution of this problem, the idea which I have discussed earlier. Actually today's concept of today's lecture was very simple, very elementary. So definitely students of any level can catch it, can get it. And in the next lecture we will again see a simple idea, but that will be very important for problem solution in simple harmonic motion, and that will be the discussion on energy of the particle executing simple harmonic motion. Okay, thank you very much.